researchers here, they are Neda Rogeni and Marco Passafiume, and they will give a talk in part 1 and part 2, which is titled FMCW, rather deterministic augmentation applied to deep learning network for classification of UAV microdoplex signature. The talk will be shared between them, and I believe Neda will be the first one. Neda received her PhD degree in electronics and electromagnetics engineering from the University of Florence in Italy. Her research interests include ground-based synthetic aperture radar, ground-penetrating radar, multiple input, multiple output radar, radar interferometry, compressive sensing, as well as antenna design. She currently works with the Department of Electrical and Computer Engineering at the University of Waterloo and Wireless Sensor and Devices Lab. Her current research focuses on radar sensors, specifically cascade radar using MIMO and informing technologies, applied also in biomedical application. While Marco Passafiume received his PhD also from the University of Florence, and actual research activities cover the developing of embedded system and digital system for communication and system on chip and system package for human interfaces devices. At presently, he's studying new development technologies based on FPGA, which cover in-depth various aspects related to computer science, like artificial intelligence and data signal processing and digital communication. His scientific interests cover many areas of signal processing and algorithm development, and now it's in particular interested in human interfaces devices and artificial intelligence applied to biomedics. Okay, so I believe that now is the turn of Neda. So Neda, please take the screen.
Sure.
Share your slide. Okay, thank you. Please go ahead.
Okay, at first, thank you so much. It's my pleasure to be here today and have this talk about one of our important research, which is by the title about considering and applying a deterministic augmentation, applying to the deep neural network for classifying the UAV by using the microdoppler signature as well as using the FMCW radar. Of course, by the title, it brings to your mind that this idea and this research maybe is just useful for the UAV classification, but to be honest, this is a new point of look at a data augmentation and learning the topics that today my colleagues, Dr. Passafiume, Marco, and I wanted to present it. We can use this method for also different application. For example, we can use for biomedical, natural environmental monitoring, weather forecast, and so on. This study was conducted when I was a researcher at University of Florence as a collaboration between my colleague, Marco, and I. And now both of us are researchers at Canadian University, Waterloo, and Toronto. And to be honest, this is also another honor by me that I have two of my supervisors here, Professor Chitronali, and recently Professor Shaker. That is a great opportunity for me to have this collaboration with their team. Okay, This talk will be divided in two sections. The first part will be presented by me, and the second part will be presented by Marco. At first, I would like to present the strategy of using data augmentation for classifying the UAV when we faced the sparse data. The outline of this talk is below. At first, I'm trying to present some critical challenges about the data scarcity and quality for training the DNN network for classification UAV application. After, I'm presenting some approaches for using and applying the data augmentation, which is, for example, using a classical random augmentation, and also using the digital twins and simulating an EM solver that we had a great presentation also before. After all, and reviewing all of this concept, I presented about our methodology, our purpose way, which is exactly deterministic augmentation. And after that, we started to review the training methodology from starting, presenting and preparing this deterministic, arriving to the final goal, which is exactly the classifying UAV. Okay, I suppose that all of RF engineers who also works with the AI are familiar with the term of the DNN. The deep neural network is a relevant topic for classification of radio frequency these days, and we all aware that the primary challenges is the trade-off between finding the data suitable for training network and the effort for required the experimental measurement. Consequently, we know that the quality and the quantity of this data set is very critical, which means that this data set should be enough and should cover a wide range of cases, but accurately represented the scenario that we want to classify. And if this condition is not met, we know that the several challenges will be happen. The important one is overfitting of the network, which means that our model started to memorize the training data and comprising the ability to generalize to new data. The other important challenges, of course, is the extensive data set. We know that the effective learning and the pattern recognition needs really a large and huge data set for the variability of UAV operation. And sometimes this is really hard. Also, sometimes we face these challenges for limited available labeled data, or actually means that the ground truth data, because we know that accurately identifying varying UAV models is really require expertly labeled data, and sometimes is hard and also so costly. The other challenges, as we know, is that because the complexity of UAV features, we know that the UAVs shows many diverse design, function, and potentials, operational behaviors, complicating the extraction of discriminative features for a good classification sometimes is really hard. And also we know that sometimes our network will be faced some challenges and affected by environmental condition. We know that the sensor data quality and then leads to the classification reality sometimes affected by this environmental condition like the weather or lightning. Okay, but what's the solution? How we can overcome for all of these limitations or challenges that we have? Our answer to this question is, of course, using data augmentation for generating a new data set and synthesizing a new data set. Okay, as we know that the data augmentation is a powerful technique to enhance the DNN training data set by creating a synthesized data samples through the transformation of existing data. and it's helped to prevent model overfitting and improving the generalizability of the network. We know that for data augmentation, there are two approaches. One, data augmenting with the data space, and the other one is the data augmenting with the feature space. When we're talking about the data augmentation with the data space, is that applying a random transformation to the input and start to produce a new data set. There are many classical random augmentation package, and we can start to apply them for generating a new data. But almost the best way is the feature space. And for the feature space, actually, we should start identifying the raw data and then combining those ones that appear to be similar respected the measurement. For this and for synthesizing this raw data and very close to the real scenario is using some EM solver like HFSS or CST and trying to designing exactly the real scenario. Okay, back to the random augmentation. We know that as I say that there are many different packages for applying a random data augmentation useful for Python. And one of the famous is the TSOC, is a perfect packages for augmenting the time series data, and is really fit for the data comes by the radar. And it has a many different methods, like for example, the adding noise, convolving the signal, pulling, resizing, reversing, and so on. But we know that, of course, the data space, data augmentation, and the randomly is very straightforward, but there are also many challenges. For example, the risk of overfitting for non-ideal features. Maybe augmentation introduces features, but this feature does not represent it exactly underlying class characteristics. And still we have the risk of overfitting. The other challenges is ineffective learning for synthetic variation. Means that randomly generated features not represented the real world exactly variation, and leading the network exactly to learn from the synthetic artifacts. The other challenges is the network aging phenomenon, and it means that continuous training over the augmented data set maybe decrease the accuracy over time as our network has started to forget the fundamental concept. The other one, dependency on the hidden features, because model may rely on the feature that are not specifically augmented the data and not generalize well the actual data. And it's lead to the poor real world scenario and also lowering accuracy for the network. The other one is negation of training memory, which means that variation in hidden feature is not reflective exactly the true class characteristic. And it's started to negation of the training memory, and again is started to decrease the accuracy of network. The misguided feature emphasis is when the network has started to emphasize in certain augmented feature and they are not translated to the actual distinguished characteristics for the target. And finally is model inflexibility, which means that over time, the model becomes rigid and losing the flexibility for adopting a new data pattern, and again, is not presented augmented data set. As a conclusion, all of this, okay, maybe using a random augmentation, we increase the data, but still is the risk for raising the meaningful data or enhancing some features that are not related exactly to the classes. So we prefer finding and going to the feature space, which of course is the better than the randomly augmenting. as I stated, we have a many solver that they started to generate it and the synthetic data for AI radar models and producing a large and diverse data set that simulated exactly complex real world condition. For example, as we saw before, the ANSYS also offer one of these packages exactly through the SPR pluses, and this technique exactly enhance the accuracy and speed. And we know that for utilizing a feature space argumenter here, at first, we should use, for example, we should use this EM solver trying to design and simulate the real world and trying to make our synthetic data for the training our network, and finally started to identify the features and combining those one related to the class and training the network, and finally using them for the testing the network in real scenario. I mean that for real experimental, the data comes by the radar. Okay, respected to the randomly augmentation, of course, this technique has many advantages. An important one is the high fidelity data, which means that we have a really high accurate simulation data and data set. The other one is the comprehensive testing, which means that it gives us this chance to testing a vast range of scenario, including some rare or dangerous one that is not easily captured in the real world. The other one, it gives to us the control over the variable, and we can check the environmental and system variable and understanding the impact of them over the system performance. The other one is for labeled accuracy data, which means that we can start to generate a good ground truth signals and using them as our data set. And finally is the safety, because sometimes this simulated and using this EM solver is good for the condition that the experimental has a risk for human or sometimes for the equipment. But of course, for each technique, there is also some disadvantage, and we have also for using the EM solver some disadvantage. The important one is that maybe initial setup cost, which means that developing a scenario and designing, especially the highly detailed ones, can be costly and time consuming. The other one is the computational demands. Of course, when we want to do this simulation, specifically for the real-time and high fidelity one, the computational is intensive and we needed very advanced and high profile system. And the other one is, of course, the time consuming, means that running simulation can be lengthy, specifically when we want to consider many different scenarios, and also the dependence on the accurate model, because we know that the effectiveness of this simulation is highly dependent on the accuracy of physical model and assumption. Okay, so we arrived to this point that, of course, the synthetic data increases the effectiveness and the speed. But this question arises here. Are there any alternative solution using exactly a real world scenario, feature space augmenting, and match and with high fidelity and quality, and also gives this possibility for controlling and different parameters, but being fasty, such as randomly augmentation? And our question to this, our answer to this question exactly is yes. And this is deterministic and model-based augmentation, the method that we propose through our study. Okay, let's go doing a comparison between this. Of course, using EM solver and using this deterministic and model-based, both are synthetically made the training data set, and they both of them works over the feature space. But the first one is exactly numerically based data set, and which means that it's a simulation, so it's need the computational it has a high computational complexity, which means that the time expensive, and also it need the high amount of the data, which means that the memory extensive. But the last one is analytical based data set, which means that just generator, just a function. And so means that it brings the low complexity because it's just an equation, and low amount of the data because it's just argument. So I should say that, so we win because we found it a way between a fastly but randomly, and the other one high accuracy and high fidelity data, but faster than it. Okay, so when we have this deterministic augmentation, let's see what will be happen. This data augmentation with analytical model started to produce a meaningful training data set where significantly reduce effort for require the real measurement data set. Again, I should mention that also this deterministic and model-based augmentation is feature space augmenter. We know that the variability for data comes by adding some noise and perturbation, and it brings some randomness to our system. But what means, I mean that I should highlight it here, that this noise added to arguments of model generator function. And this argument model generator exactly define this feature space. That means this noise actually increases the signal variability in pseudo-deterministic way. But what means this model generator? Model generator is simply a function which depends on the physical parameter are targeted. For example, in UAV, the engines of the UAV. For example, it can be like a digital twin or other, I mean that EM solver, or it can be exactly a deterministic augmenter. But please, attention here, because we should be really carefully about one important parameter, which is the noise variance and noise variance of feature, because it's very critical, and it should be significant enough to bring and capture the variability within the target classes, while should be exactly limited enough to prevent, to spread the data samples that could be incorrectly classification. So for this reason, this is very important parameter for us. Okay, based on this talk, and as I say that, our deterministic model is just a function argument. And for UAV classification, it comes by the effect, exactly the effect of the microdoppler signature of flying UAV. And this equation totally depends on the target physical parameter. For example, the RCS of each engine for the UAV, the mechanical and vibration parameters like the amplitude, phase, and frequency for each engine. And we adopted such a model as a data augmentation between the feature space model dataset exactly through this using noise variance. Please give me a stop here, because the second part of this talk is exactly to talk in detail and presenting the math behind of this model augmenter. Okay, imagine that we have our data augmenter, and what's next? What's So it means that no, we are ready for starting and training our network. I should say that our training methodology has a 5-step from the first to arriving to the final goal, which was a classification for UAV. The first step was the radar data acquisition, and the second step, which is exactly the topic for the next part of this presentation. And as I mentioned, that an important parameter which started exactly to fit this deterministic model to the exactly our scenario was the parameter of sigma p. And for this reason, one important step for us was finding the optimum value for this sigma p. And after introducing our CNN network, and finally is the classification of UAV. The radar acquisition was our important step, one of our important steps, and it started to generating exactly some real measurement captured by the 77 gigahertz FMC frequency, which it had 8 receiver and 4 transmitter. Here you can see that the flow chart of this radar data acquisition. We had our radar platform and start sending the signal and having the T exchange and receiving by R exchange. And of course, because of all information, the physical parameter that we catch for introducing and presenting our model comes by the target signature. So which means that we need the range profile information, and by this applying some signal process algorithm like a FFT, fast Fourier transform over the fast time, we started to catch our catch our data. I mean that the physical parameter. And here you can see some plot regarding this range profile, as well as the radar images, applying MTI and without MTI. Okay, as I said, this model is really dependent on the physical parameter of the target, which means that for mechanical or vibrational parameter as RCS or amplitude, phase, and so on. So we started setting capturing our data set, the real raw data captured by the radar, in 2 different sets of UAV, which was, for example, a quadcopter and a single rotor. Then we started to exactly extract our target signature and using our model and trying, model fitting for our scenario, and I started to generate a synthesized data set. And at the end, we started tested our network in different set of UAVs, which was exactly as a matter of the engines, the same prototype like a quadcopter and single, but totally different size and totally different material and different shape. Okay. Escaping from the step 2, because the step 2 is exactly what math behind this equation. We are going to the finding and obtaining the optimal value for the sigma parameter. As I state that it's very important parameter. So we started to consider different value from 0 to 0.6 randomly, and started using 3 different machine learning algorithms such as a SVM, ground boosting, and naive Bayes, and starting to training our network and finding the classification accuracy and finding what is the best and optimum parameter for generating and synthesizing this new data set. In our scenario, we found that the 0.2 is the best one. But look at this plot. I mean that the plotting for the accuracy and the different sigma p is very interesting, because if we consider the 0 for this parameter, means that no augmenting. And this graph shows to us after 0.3, the networks and accuracy is almost like a steady, because we face it exactly generating an overlapping features for our classes. Here, look at, there is for example, a two-dimensional classes for classes that we have, A and B, and you can see that the good value for the sigma is between the center of the probability for the classes B till exactly the hyperplane and the decision method for us. If we started to increase this one, we started to go to the bad sigma value, and what will be happen? As I said that, exactly, our features overlap with the class A, and it started to decrease the accuracy of our classes because we overlap, and such as like an overfitting for the network. Okay, as you can see here, we presented our value using exactly 3 different SVM, applying different sigma. And as I stated, that the maximum and the best, the maximum accuracy comes by the parameter sigma p equals 0.2. And it's interesting that also for all of this network, this SVM ground base and also the naive base, we started to train our network using one different set of the UAVs, and then started to train and started to test it our network exactly with different set of the UAVs, totally different material, but quadcopter and the single was as a matter of similarity between them, as well as training one time the network with the mix of both of these and testing in the part of the other data again as a mix of them. And you can see that for all of them, the sigma p equal to 0.2 was the highest accuracy between the other. Okay, so I suppose that now we have our model and we have the best and optimum parameter for the sigma p. Now we generated a huge bond of the data set, near 32,000 signal, which each of them has 400 features. And the fantastic point was that just less than 30 minutes for generating them. And imagine that if we want, for example, using any other EM software, and we need maybe 30 minutes just for generating each sample and signal for exactly 32,000 sample, means that we need near 1.8 years. And this is the advantage of this way, means that really we decrease the computational time as well as the memory expensive. After it, and when we generated our data set, we started to introduce our CNN network. Our network was very simple, including 2 layers of convolutional and the pooling layer. And at the end of the feature extraction was the flattened layer, which started to convert our features to the vector and sending to the classifier. And our classifier was included 2 fully connected and the classification module. We used the activation function, the ReLU, for our network, and our last function was the cross entropy. And the softmax helps to us to convert the raw score to the probability, and it started exactly to do the classification process, which means that, for example, the quadcopter or the single rotary. And here you can see the result of this study. At first, we started to split our data set, 32,000 sample data set, to 3 different parts. the training data set was 80% of this data set size. And for validation, we use 10% of this data set. And finally, for the test data set, covers exactly the 10%. Our model trained with a back projection algorithm, and the learning rate was here 1,000 millisecond. And here you can see that the result of the network trained with exactly a synthesized data generated by our model-based augmenter, and then started tested for the real measurement, but for the another set of the UAV, as I showed you. And you can see that the accuracy was 78.68% using only 50 epochs. And also, again, as a comparison, we started also train our network using a random augmentation, the TSOG packages, of course, with more epochs, 100 epochs, and you can see that still the accuracy is really low respected to our scenario. And it was 66.80%, near the 12.5%, we increased the accuracy. Far from it, also by the classification precision, also you can see that although maybe still the accuracy is almost the same, but with the network shows that deterministic augmentation shows and exhibit a far lower classification bias respected using random augmentation. And I can say that we win because we decreased computational, memory expensive, and generated a synthesized data exactly matched with our scenario and close to the real world condition. Okay, and next is the second part of this talk, which my colleague will be presented about math behind this deterministic augmentation.
Okay, Neda, thank you very much.